So thank you, Roya, for that very, very kind introduction. It's a pleasure to have the invitation to come here. Roya and I have sort of known each other and intersected for many years, and have kind of recently had our sort of research paths cross, and I think we'll hear a little bit about why that is today. So today what I want to tell you about is some work we've been doing and some things we've learned about the interplay between geometric frustration and self-assembly. And this is work we've learned largely through theoretical modeling of these systems. And if you sort of fall asleep from sort of here on out, what I want to make sure to communicate is the following. So it's often thought, at least in sort of the material science world, that if you have a system that you want to self-organize, geometric frustration is very bad, right? It's a negative sort of impact on your material. That's to say, if you have a frustrated assembly, you're going to get an imperfect or disordered structure, okay? And what I want to try to convince you is that no, in fact, geometric frustration perhaps is leading to sort of new regimes of physical behavior for how frustration impacts materials and physical systems. And maybe if we can sort of learn the rules and principles behind how it sort of how it works, we could sort of use it to design new types of materials, right? Where we use geometric frustration as a design parameter. So let me begin by trying to define some of these terms, at least how I want to use them. So I'm going to talk about two things, self-assembly and frustration. So first, let me tell you what I mean by self-assembly. So for me, self-assembly is going to mean equilibrium assembly, spatial or orientational organizational states of individual subunits that form typically from a kind of disaggregated or dispersed state. So in this kind of cartoon model, I want you to think of this kind of puzzle piece that's been designed to fit together into this sort of 2D lattice. And at some finite temperature and concentration, there'll be some steady state equilibrium between the disaggregation and assembly, okay? And so the systems I'll be talking about today are usually, the self-assembly is taking place around room temperature, and so therefore they're what we call soft materials, things like biological materials, okay? And so what types of systems self-assemble? So some of you might be familiar with this, but these are some of the usual suspects of soft matter systems that self-assemble. So on the left here, this is an example of lipids or surfactants. These are molecules that have a charged or a polar part and an oily part. And if you disperse them in some aqueous or polar solvent, they can spontaneously organize into clusters or structures that try to hide their oily tails and put their water-loving heads in exposure to that solvent, okay? But the way in which they assemble, they can organize into different structures, so they can form these kind of clumps, which could be either spherical or cylindrical micelles. They can form sheets, or in fact, these sheets can fold up and curve into three-dimensional spheres. This is called a vesicle or a liposome, depending on your community. And to a first approximation, this is kind of the structure and composition of the sort of plasma membrane of eukaryotic cells. So biology, of course, also uses other types of self-assembly. So here's an example of an assembly of many proteins that have assembled into this beautiful icosahedral cage. This is the protein shell that forms the viral capsid. In this case, I think this is Cowpea mosaic virus, maybe? No? And this is a much larger virus that can harm you and I. But what's sort of essential here is that the sort of genome is encoding for folding this three-dimensional object and programming its interactions in some directional way to fold up into some well-organized state. Okay, and this is not just the process that's used to give shells and viruses, but it's used in you and I to form assemblies of long filamentous proteins and other sort of protein superstructures in our bodies. And over on the right here are some sort of synthetic analogs, if you like, to these materials. These are colloidal systems. They're made in chemistry labs. Particles that are sort of tens to hundreds of microns in size, just small enough to stay suspended in solution. And if you're a fancy enough synthetic chemist, you can introduce patchiness into the structure of these particles such that they're programmed to interact in a very specific and directional way that kind of mimics the way we think that protein complexes interact in these folded structures. Okay? So the sort of key ingredient across all of these materials is that you have some sort of physical non-covalent interactions that sort of guide the structure, at least on some local scale, and that cascades into some self-assembled structure. So what I want to talk about now is this sort of second thematic ingredient is this is geometric frustration. So first I'll sort of step back and try to introduce a more canonical definition of geometric frustration. And this term geometric frustration was introduced by Toulouse and sort of became very popular in the late 70s in the context of spin lattice systems. Okay, and so the basic idea is that the definition is you have some local order which cannot be compatible with propagating through the global constraints of space. So, the sort of first counterexample is an unfrustrated system. So let's think of an Ising system, where you have spins on some, for example, an infinite triangular lattice. Spins can be up or down. If you have a ferromagnetic system, the spins want to be parallel. There's no problem to do that on a triangular lattice, but there are only two ground states, all up or all down. Okay, this is no frustration. So how do we introduce frustration? Well, if we flip this exchange coupling so that we actually have a preferred anti-ferromagnetic alignment, okay, you can sort of see by this example, these two nearest neighbors, they're anti-aligned, but we don't really know what to do with this third one. Okay, it's sort of you know, damned if you do, damned if you don't. So either we can be anti-aligned along this direction or anti-aligned along this direction. So what comes out of this frustration is a number of phenomena, including an extensive number of degenerate ground states in these systems. So I want to talk about a kind of a more general kind of formulation of frustration, which can occur for systems like assemblies that don't have a lattice order a priori. So how do you have geometric frustration without a lattice? And so this is a notion of frustration that's sort of been extended to this kind of spin lattice sort of canonical example to systems that can sort of self-organize in three-dimensional space. And this is kind of a concept that's been extended by people like David Nelson and Maurice Clément, also around the same time as the work on the spin lattices. And basically, the idea is that you have some type of local organization in your material that's incompatible with the geometric constraints of Euclidean space where you and I live. Okay? And so the sort of, perhaps the simplest illustration of this is a model of what's called polytetrahedral order in amorphous spheres, but basically this is just a disordered arrangement of spherical particles initially introduced as a model of metallic glasses. And basically the idea is the following. Let's imagine you have a physical interaction where you want a state to have the densest possible arrangement of spheres. Locally, if I have just 4 spheres, I know exactly what to do. The densest local arrangement is just a tetrahedral packing where each of the centers of the sphere sits on the vertex of a tetrahedron. So now the problem becomes when I try to take that motif, that tetrahedrally close path structure, and build it up into some space-filling arrangement. So if I try to take this single tetrahedra and fold it around into this tetrahedral bipyramid, okay, or pentagonal bipyramid, you see that if I have perfect tetrahedra, there's a little gap. Okay, so Euclidean space is not quite just right? It's close, but not quite there. Okay, and in fact, as you start to try to pack more and more spheres here, so here's an example of an icosahedral arrangement of spheres. This is one sphere in the center with 12 neighbors on the outside. This is mathematically known to be the locally densest sort of Voronoi cell that you can get in 3 dimensions. This also is not compatible with perfect tetrahedral order, but even worse than that is there's no way to fill space with icosahedra without introducing gaps in between them. Okay? So what people realize is that, in fact, well, if I can try to do this structure locally, but now I want to sort of fill space with this, what I'm going to need to do is introduce sort of defects, right? Deviations from this sort of 5-fold pentagonal defect. So for example, one can try to construct a space-filling structure out of some of these subunits plus some of these 6-fold pyramids, a couple of these 4-fold pyramids, right? And fill space with them. And each of these defects, in fact, is associated with something called the topological charge. And what you can show, and what these co-authors showed, is that, in fact, in 3-dimensional Euclidean space, you actually need a finite density of these defects. Okay? So the outcome of this this sort of perspective on frustration is that what it does is it introduces some incompatibility that on some scale not much bigger than the building blocks is sort of immediately resolved by what are known as topological defects. So the way the system solves the problem in fill space is an extensive array of defects that pervade the system.
So, I mean, for instance, in spin glass, you have frustration and disorder, and you have two different aspects.
That's right. And so these.
So here, you're saying that those two things are coupled together. Is that the idea? That the frustration.
So the model here, and I'm not necessarily a proponent of this interpretation, is that this sort of local frustration is a generator of disorder on a larger length scale. So in fact, you can have ordered arrays of defects, if you like, and these are associated with what are known as kind of Frank-Caspar crystalline lattices. And the hypothesis was that at some high temperature, you could have some phase transition where you get a disordered array of these vortices or defects, disclination networks, if you like. And I guess I should following on that point, I should emphasize here that unlike many of the sort of uses of frustration in spin glasses, this is, in some sense, the frustration is uniform, right? It's the same amount of frustration everywhere in space, but we'll come back to that point. Okay, so here again, the key idea is that in order to fill space, you need to have a finite density of defects. And so what I want to talk about today is a different class of systems that I call geometrically frustrated assemblies. And these are different in sort of two ways. I mean, first of all, again, they're formed by building blocks themselves, so there's no lattice order a priori. They can decide to be a lattice if they want or not. And more fundamentally, what's sort of essential is that they're not necessarily bulk, right? These structures can assemble, and they can assemble to some finite size and stop if they want, right? And so, again, to sort of illustrate why that might be important, what are the new kind of physics that emerges from that, I want you to come back to this kind of this toy model of this self-assembling puzzle piece. It's, again, you should think of these interactions here between the edges as kind of cohesive bonds. And this is a puzzle piece that basically in its kind of ground state has no problems. There's no conflicts, right? It can order into a perfect two-dimensional lattice. And what that means is that once you get away from the boundary of this crystal, if I look anywhere inside of this structure, the local environment is uniform, right? So away from the boundaries, there's sort of no scale. There's no way to know where you are inside of that self-assembled structure. It's sort of uniform or scale-free. And what I want to sort of contrast this with is a counterexample where I take my puzzle piece, right? And you can sort of imagine doing this. In fact, I encourage anyone to try this at home. And you sort of make it misfitting, okay? So I take my sort of my rectangular puzzle piece and I warp it a little bit, such that if it were rigid along one direction, the rows of that puzzle would curve, okay? And as I said, I encourage you to sort of try this out at home. You can very easily show that this structure could assemble, for example, in one-dimensional chains that either go this way or this way, okay? If it's perfectly rigid, however, there's no way to avoid the fact that you have all these dangling ends. In fact, you have a number of dangling ends that grows with the number of particles, right? So you're losing a lot of cohesive energy. As a counterexample, you can imagine a different scenario where I have building blocks or interactions between those building blocks that are soft. They're soft in the sense that they can tolerate some measure of misfit, at least on some local scale. Okay, so again, in this toy model, let's imagine that I have these tapered, ill-fitting puzzle pieces, right? But they're made out of some elastomeric material. Okay, so if the cohesive energy to join them together into a cluster is sufficiently large, right, it'll be worth it for the assembly, the thermodynamics, to deform those puzzle pieces into compatible shapes. Okay, so you can imagine such an arrangement that might come out of that would be a cluster like this. And here, what I'm trying to show is that in the middle, these puzzle pieces are very angry, so they're red, right? They've been deformed away from their ill-fitting shape. But puzzle pieces near the edge, since they have fewer nearest neighbors, fewer constraints, they're allowed to relax more than the ones in the middle. So what does this give you? This gives you a structure that forms purely through nearest neighbor interactions, but can have a gradient that can extend across the structure. Everywhere inside of this material, it's different. Okay. So what emerges from this is a number of very interesting properties that I want to tell you about today. And the first I really want to kind of sort of highlight before we get into the specific examples is the following, kind of where I think this concept might eventually be useful. So let's sort of start by thinking about what is the thermodynamics of self-assembly of one of these clusters. And again, thinking back in this sort of simple, unfrustrated model, we think of the free energy, the energy as a function of the size of, say, a square domain. If we, again, attribute some cohesive energy to each of these bonds and the nearest neighbors, the free energy in 2 dimensions is always going to look like this. There's some negative free energy gain to self-assembling because there are an extensive number of bonds formed on the inside of the material. But at small sizes, there's some positive surface energy costs or line tension costs due to the unbound nearest neighbors at the outside. Okay? So in general, you're always going to have what's known as this kind of classical nucleation model that beyond some critical size, as this structure is trying to grow to sort of minimize the free energy, there's nothing to stop it. Once it gets over the barrier, it can grow to infinite size until it depletes all of the material. Now, what I want to tell you about today are a class of systems that have the following sort of different behavior. Okay? And so what happens now when we introduce the type of, there's a question in the back. So I dropped for this sort of first presentation, I've dropped the entropic contribution. One could imagine, if you like, we're considering this a free energy per cohesive bond, or if you like, free energy per subunit. Okay. We'll come back a little bit to the entropy, but most of what, just to kind of get ahead of your question, most of what I'm going to talk about are thermodynamic ground states of these systems and what we know about it. So, and I should mention, if there are other questions that would be helpful to clarify, please do interrupt. Okay, so this is the free energy associated with the cohesion of an edge of a compact cluster. But now what I want to talk about are assemblies that, if they're flexible, there can be some elastic cost that allows them to deform together into a fitting assembly. So you could think about this for this sort of tetrameric cluster that I have to squeeze these 2 bottom blocks, and it's going to pay some finite amount of energy. So what I want to tell you about are models for which the free energy as a function of size is going to grow. It's going to grow with a number of parameters. One, you can expect it'll grow somehow with the stiffness of those building blocks or the interactions that are holding them together. But it's also going to grow with some strain in this assembly. And there are at least a handful of examples, sort of 10 or so, where we understand that this strain can be written in the following form. That's to say, it depends on the amount of frustration in these assemblies. So in this case, this phi is some geometric parameter that if it's 0, if it's unfrustrated, as I tailor it away from 0, I'm increasing frustration in some controlled way. And the strain of that assembly will grow as a power law with the size. And this can be different power laws for different sort of types of order the system is trying to establish in the assembly. So what that amounts to is, in addition to this cohesive energy gain, there's an elastic energy cost that can grow as a power law, at least over some size range. And what you get in that case is a total free energy as a function of size that looks like this. Right? This elastic energy cost can prevent the structure from ever reaching this kind of cohesive energy minimum due to the fact that as this structure is growing at the boundary, eventually the deformation is so large that this particle here says, forget it, I'll start my own cluster. Right? There's not enough cohesion to convince me to join that assembly. And so what we proposed is a kind of a schematic phase diagram at this point that looks something like this, where we can think of the phases of self-assembly in the following way. On one axis, we have the ratio of the cohesive energy gain versus this elastic stiffness. On another axis, we can think of frustration as being some control parameter here. Again, what is frustration in any example is an important question. But the basic idea is that if you exceed some critical value of frustration, you can open up an equilibrium thermodynamic window where there's an equilibrium phase where these clusters know how big they are. They have a finite self-limiting size that's much bigger than one building block, yet less than infinity. Right? And so I want to convince you that this is a very weird thing, right? Because this process that I'm envisioning is really the interaction of, if you like, local interactions between nearest neighbor building blocks. There's no obvious long-range forces in this system, yet somehow these local interactions have a way to sort of measure the structure. Okay. And so what we were interested in, of course, is like, okay, what can we learn and say about this? And before I go on, I want to a little bit contrast this with some examples where we already, if you like, have equilibrium assemblies in soft materials that have a self-limiting size, which many of you may be familiar with. So the first of one are these amphiphilic assemblies. I told you about them a few slides ago. These are these, if you like, these polar molecules. They can form these kind of compact sort of spherical or bilayer systems. And you could look at this and say, well, this is self-limiting in the sense that it only grows sort of 2 molecules thick. Okay, and that is indeed true. However, what you realize in this example is that what's limiting the assembly size is the size of the building block itself, right? The size of the molecule that's sort of reaching from the inside to the outside. So if you wanted to build a bigger assembly, you need a bigger molecule, okay? On the other hand, there are self-assembled systems in some unusual colloidal systems, and this is actually related to a model of, I guess, what's known as nuclear pasta, where you have short-range cohesive interactions, but long-range repulsive interactions, okay? And so you can show in these systems that the free energy as a function of size exactly has the form that I argued to you for these geometrically frustrated systems, where this long-range repulsive buildup is now coming from, if you like, the self-energy associated with the Coulomb repulsion in this system. So this is actually very difficult to achieve in a laboratory because it requires you to go to weird solvent systems where you have a very low number of mobile counterions that can screen away electrostatics, okay? So what it requires is that you have interactions that are repulsive on length scales much bigger than the building blocks themselves, okay? So if you have local interactions, this doesn't work. And finally, there's kind of a new class of materials, of designer materials, and I sort of struggle to kind of explain how this works in a short amount of time. But essentially, the idea is that people have kind of leveraged sort of advances in DNA technology to make really cool and amazing systems where you can get a number of different species that are functionalized with DNA in some way, such that A particles like B particles like B prime particles, but they don't like C particles. You can program this matrix of interactions such that you can target a precise three-dimensional structure in equilibrium, okay? And supposedly, if you do this well, you can target only that structure and don't make errors, and that's a whole kind of challenge of how to realize these assemblies in high yield. But what's essential in this sort of paradigm is that if you wanted to build a structure that's sort of 10 units wide in its self-limiting size, you need a number of species that grows with that self-limiting dimension raised to, I don't know, some exponential power. Okay. So if I wanted to make a structure that's bigger, I'm going to need to mix a number of species that's going to grow with that self-limiting size, sort of arbitrarily large. Okay. So what's different about geometric frustration and how it may operate here? Well, first, you can have equilibrium sizes that, unlike surfactants, are in principle arbitrarily larger than those building blocks themselves, much bigger than the molecules or the bricks. Okay. Only in principle through finite or nearest neighbor interactions, right? Local interactions sort of give rise to the sensitivity of size, and in principle from a single species of building block. Okay, and so I think these are some of the properties that sort of distinguish this kind of mode of assembly from other types. So this is the background, and what I would like to try to tell you about is some of the following, and we'll see how we do on time. So what I want to do is tell you what we've learned about self-limiting assembly and the kind of the basic physics of this through 2 examples that I consider sort of prototypical models of geometrically frustrated assembly that people have been studying in the laboratory and in simulations. And then I want to tell you about sort of other types of phenomenon that arise when you have a system that self-assembles in the presence of geometric frustration, because like you and I, you know, if there's one path to go forward which is sort of subject to lots of constraints that you don't want to deal with, what you would try to do is find another way, right? You want to find a way to escape the problem, okay? And so it turns out that geometric frustration can trigger a whole range of what I'll call kind of morphological responses that are, in some sense, ways that the system is trying to escape, okay? And it's sort of essential to sort of understand how these function if we want to understand anything about, say, for example, how frustration establishes a sort of size control in these materials. And if there's time, I'd like to tell you a little bit about some open questions and challenges, things that we don't know, which is much more than we do know. Okay, so this is the roadmap. So let me begin with sort of 2 model systems. The first one I'll call the geometrically frustrated prototype A. And this is an example where I am trying to form a self-organized crystalline assembly, right, like a hexagonal crystal, and a topography which is required to be spherical. Okay? And there are some examples of this that arise in lipid vesicles. So for example, you can have lipid vesicles that are composed of two types of lipids. One type of lipid will form a fluid phase, while the other type of lipid will form a crystalline phase. So what you should think of is this kind of sphere here as being composed of these little solid crystallites floating on this sort of two-dimensional spherical fluid C. And recently, people have realized sort of experimental systems. So these are polystyrene spheres that form crystals at the interface between an oil and liquid droplet. Okay? So we can now start to do these experiments in laboratory to understand how frustration impacts these materials. So first, let me try to give you a sense of like what's the problem with frustration and how do we think about it? How do we think about understanding it in a kind of a physical perspective? So the way I like to think about it is imagine that I first form a hexagonal crystal where what I'm not showing you here are a bunch of subunits that are equally spaced. Okay, there's no stress in the assembly. And now I'm going to sort of project it or force it onto a sphere. Okay? And you could do this experiment with a piece of paper and put it on your head. I assure you this is true. That if I try to enforce this flat sheet onto a spherical surface, I can't simultaneously keep the length, if you like, of the radius the same as the length of the perimeter. Okay? What this means is that I'm going to introduce geometric compression, if you like, along the latitude of this projection. Okay? That's going to kind of squeeze the nearest neighbor spacing at the outside. Okay? And of course, people who, cartographers, they know this, right? This is known as a result of Gauss's theorem egregium. There's no way to sort of take a map of the Earth and deform it to a flat surface without distorting the continents and the geodesic distances in the map. But it has a ramification for these self-assembled structures. So here, this is a simulation model of a spherical crystal that's roughly circular in cross-section. Okay, it's just a simple bead spring model. And here it's been colored according to the sort of local spacing between the nearest neighbors in equilibrium. And what you see is that at the outside or the perimeter of this crystal, the distances between those nearest neighbors are closer together than they want to be, this equilibrium spacing D. So we have compression. And at the inside, we have tension. Okay? But what you see just visually looking at this map is that everywhere the sort of local packing from the inside to the outside is inhomogeneous. Right? So every sort of structure inside, every piece of the structure sort of knows where it is kind of globally throughout this assembly. And so the way we think about the mathematics of this is through this relationship here, which in the context of mechanical engineering is known as the Foppel-von Carmen equation. And what does it do? It relates the stress in a sheet, in a plate, okay, that's sigma, to the Gaussian curvature that you've subjected that sheet to. So what is the Gaussian curvature? The Gaussian curvature, it's the product of the two principal curvatures measured in perpendicular directions on a surface. Okay, so for example, if I have a saddle-like surface, the Gaussian curvature is sort of down in one direction and up in the other direction, so the product is negative. Okay? If I have a spherical surface, the Gaussian curvature in both directions is the same sign, so it's positive. Okay? So this Gaussian curvature for the sphere, it's 1 over r squared. So what does this equation say? Well, it says that if I have Gaussian curvature, right, the right-hand side of this equation is not 0. The left-hand side has to not be 0. That means I have to have gradients of stress. Okay? Not only do I have to have stress, but I have to have stress that is different from the inside to the outside of the crystal. Okay? And for those of you in the audience, what I really want you to think of this is kind of like what you might see in sort of a theory of electrostatics. Okay? So here the stress, this is like the electrostatic potential. And Gaussian curvature, it's acting like a source for stress, like a charge. Okay? So we'll come back to that analogy a little bit later. But so the solution of this is to say that the stress inside of this crystal, at least the magnitude of the stress, it grows with the size of that crystal, in this case W. Okay? So macroscopically, the stress everywhere somehow has a way to measure how big the entire assembly is. Okay. So what are the consequences of that? So again, let's go back to the thermodynamics. And let's think of now a model where this spherical patch is assembling. and it's in equilibrium with some reservoir of if you like, free subunits. So it can pay some amount of free energy, if you like, for sort of reducing the entropy of those free subunits, so that can go into some chemical potential for forming a crystal. Okay? But again, we have these kind of three ingredients. There's the bulk free energy gain of crystallizing. So if delta mu is positive, it's favorable to grow a crystal, if it's sufficiently positive. There's some line tension associated with the loss of cohesion at the boundary. And in addition, there's this elastic penalty that goes as this square of the stress. Okay? And the stress, as I showed you, is growing as the power law, W squared, with the size. Okay? So as this system is assembling under a large drive for crystallization, it's going to be a fight between this bulk energy gain and this elastic energy growth. Okay? And so it's not too hard to imagine that this sort of balance between these two terms, if you say just minimize these two terms and forget about line tension, is going to be something like this, where the equilibrium size is going to be inversely proportional to the elastic modulus of that crystal. Okay? And so if you take this model, where we've made a number of kind of crucial assumptions, and I'll try to come back to these. First of all, we've assumed that the sphere is a strictly rigid shape. So frustration is unavoidable, right? It has to assemble with a fixed radius. This is the type of phase diagram you get. So again, curvature on one axis, the increasing kind of cohesive drive for assembly. There's only a dispersed phase and a self-limiting phase. And across this self-limiting phase, the equilibrium size is continuing to grow. Here, for the moment, I'm ignoring the fact that there's actually kind of a finite area of space that any crystalline patch can occupy due to the positive Gaussian curvature. Okay, so let me put that aside for a moment, and I want to introduce a second class of models, which initially looks completely different. Okay, I want to tell you that, in fact, there's a kind of a secret connection between them. I'll share with you that secret. This is a model of what we call chiral filament bundles. So this is a rope-like assembly of one-dimensional threads. We're motivated to think about this by numerous examples in biological materials of proteins that form one-dimensional filaments, and then those proteins come together and stick together in what I would call these sort of self-spinning fiber-like structures that have a coherent twist to them. Okay? So you can see this, for example, in collagen fibrils. Collagen is kind of a principal component. In fact, it's the most abundant protein in our body. And many times, collagen is forming fibers that reinforce our cells and, our tissue and bone. Fibrin is a protein fiber that forms blood clots. Okay, and the way it forms blood clots when it coagulates is it forms these cables, and the cables are observed to twist. So what's important about this structure is the following. It's not the Gaussian curvature of the assembly, but it turns out to be related to what we call the twist of the assembly. So I'm going to parameterize the twist by this parameter omega, but omega is just like, it's just 2 pi over the helical pitch of this structure. Okay, so it's an inverse length scale. So I said this is a self-assembled structure, and it's twisting, but it's not like a textile material that it's been twisted by hand through the manufacturing process. It's somehow twisting itself upon assembly. So where does that twist come from? So I'm going to take a kind of quick digression to introduce some old characters. So what is the origin of twist in these self-assembled materials? So this is related to something called chirality transfer. So as many of you know, or many of you don't know, chirality is a property of objects, including molecules, that is defined by the sort of lack of mirror symmetry between two objects. So if I take two objects like my right and left hand, okay, I can't superimpose them on one another. Okay? They're mirror images of one another, okay, under any uniform translation and rotation. And chirality transfer refers to the ability of the self-assembly to transfer that lack of mirror symmetry to the assembly itself. Okay, so if I have right-handed molecules, I get a right-handed assembly. If I have left-handed molecules, I get a left-handed assembly. And what's amazing, of course, is that the building blocks themselves can be quite small, molecules, and the assemblies themselves can be millimeter scale, kind of orders of magnitude larger. And so you have kind of a vast kind of range of length scales involved. And so the canonical example of this is Pasteur's discovery of the right and left-handed crystalline habits of tartaric acid precipitants, based on which, in part, he hypothesized the existence of right and left-handed forms of molecules. But sort of since that time, people have discovered numerous examples of how chirality transfer appears in all sorts of self-assembly, everything from chiral lipids, okay, that form spiral assemblies, to protein assemblies. So proteins are inherently chiral building blocks. So my favorite example of chirality transfer is shown here. It's very hard to see, I'm sorry, in this micrograph, but what you're looking at is an image of a cholesteric liquid crystalline texture of DNA oligomers. So if you take short strands of DNA and you concentrate it at sufficiently high concentration, it forms a phase where all the molecules are pointing locally in the same direction, but that direction is sort of rotating in a handed fashion, transverse to the molecular backbone. Okay? And so people in the field of liquid crystals have realized that this can be associated with a sort of a preference for chiral gradients of this orientation of these long molecules. And in fact, you can translate that same sort of point of view to assemblies of, if you like, rope-like assemblies of these twisted molecules. So these are biological building blocks. It's believed they have chiral interactions that lead to a spontaneous preference for local skew between the threads of this structure that gives rise to the chirality transfer to the assembly. Okay, so what's important for what I want to tell you is at the following is that there is some chirality in this, the assembly, and there's some free energy gain to be had if the structure can form in a chiral way. So what does this have to do with frustration? So one way to think about the frustration is through this kind of example here. You imagine you start by looking at a slice through one of these kind of perfectly ordered bundles, and I'm going to impose this chiral twist. You can see from this picture here that these filaments at the outside, they start to overlap. Okay? And that's simply because those nearest neighbors are tilting towards one another. Okay? But they haven't gotten out of the way to make room. Okay? So this doesn't look anything like the problem I told you about before, but it turns out that there's a deep mathematical connection between these two problems that has to do with the properties of what are known as Romanian Vibrations. Not necessary to go into the details, but what's important to recognize is that the distance of closest approach between the threads or columns of this sort of helically twisted assembly, right, this distance delta, that maps 1-to-1 onto the geodesic distance between sort of equivalent points onto a sphere where the radius of that sphere has some relationship to the helical pitch of the assembly. So what does that mean? It means that there's no stress-free way of packing the interfilament spacing in this twisted assembly in sort of precise analogy with the way that there's no stress-free configuration of a crystal on a curved surface with Gaussian curvature. Yes, Raya?
This is because each one is chiral, or you're just...
It's because the kind of global constraints of the chiral assembly itself. So if you like, there's a hierarchy of energy scales sort of assumed in this model. The first is that there are each one of these fibers themselves is chiral, and that creates a drive for a global twist of the assembly. Okay, and it's that global twist of the assembly that frustrates the interfilament spacing. Okay, at the origin, at the bottom, of course, it's coming from what's believed to be the intermolecular forces, although you can show, in fact, in a laboratory that it's also true if you just take a bunch of fibers and twist them, that if you measure the distance of global distance of closest approach, it maps 1-to-1 onto this non-Euclidean metric, which I could tell you about some other time. So what's nice about this is that, so we sort of think, well, we understand something about this problem, or at least that's what we told ourselves at the time, so now we can just kind of borrow the technology, right? So the relationship between curvature and stress should be something like the relationship between twist and stress, okay, in this bundle. And again, you know, there's some sort of correspondence between what the kind of physics of these assemblies and physics of again, assemblies that initially don't look very similar. Okay, they share some sort of residue of frustration. So what's a consequence of this? Well, here what I'm showing you is an example of a simulation of the cross-sectional order of a twisted bundle. I will try to tell you about the details a little bit later in the talk of how the simulation is done, but essentially what it's doing is taking this bundle, imposing twist, and minimizing the cohesive energy subject to pairwise interactions that depend on the distance of closest approach between the fibers. Okay? And again, it's colored according to, if you like, the local tension and compression in the assembly. And so what you notice immediately is that this pattern of interfilament strain, interfilament deformation, is exactly the same pattern that we observed in the crystalline cap assembly. Okay? Things are too close together at the outside and a little bit stretched away from equilibrium at the middle. Okay, and so this is, again, the metric frustration associated with the fact that I can't simultaneously twist and equally spaced filaments in a two-dimensionally ordered material. But filaments, bundles, are not exactly the same as crystalline caps. They're really sort of three-dimensional materials as opposed to a two-dimensional crystal. They have extra degrees of freedom. Okay, and so in fact, they're subject to an additional layer of frustration that is no counterpart in the crystalline cap. So it's sort of obvious when you just look at a kind of a model of this that the filaments that are in the middle of this structure, they're sticking relatively straight up, whereas these filaments at the outside, they have to curve more and more to conform to this kind of quasi-cylindrical geometry. So if you consider some energy penalty, as you would have for flexing an elastic beam, okay, which is intrinsically straight, but I can pay some mechanical cost to bend this. There is also a frustration of the, if you like, the intrafilament shape. The filaments want to be straight, but they can't be straight in this configuration. In the middle, they're straight, but at the outside, they bend. Okay? And so both of these sort of power laws grow with twist, but it turns out that they depend on size in different ways, and for some properties, that's important. Okay? So what happens if I now ask the same question for the self-assembly of chiral filament bundles? Well, it's going to look fairly similar to the self-assembly of these crystalline patches, except what I really should do is think about minimizing not the free energy, but the free energy density, because these structures are unlimited in length. Okay. So let me consider a bundle which has a radius r. This is not the radius of a sphere. It's the radius of a bundle. I apologize. Impose twist, some surface energy due to the fact there are fewer nearest neighbors at the boundary, and some bending stiffness for bending these filament bundles. So what you see is that there's a handful of these elastic terms. There's some bending energy that grows with the size. There's some interfilament packing energy that grows with the size. They both are only non-zero if it's twisted. Okay, but they grow with different power laws with size. And the sort of crossover between them introduces kind of a characteristic length scale, or at least it's defined by a characteristic length scale that you can think of as arising as the sort of ratio of the sort of interfilament bending modulus divided by the interfilament packing modulus. So this, you might call this the sort of bend penetration length if you're kind of familiar with that sort of terminology. So these are the terms that resist assembly. What drives assembly is the drive to minimize the surface energy cost, right? The amount of surface energy per unit volume would favor this bundle to be macroscopically large. Okay, so what restrains it are either bending or packing, and what you'll find is a self-limiting equilibrium size, which is either larger or smaller than this critical radius. So for now, let me just introduce this critical size as a way of telling you whether, if this equilibrium bundle is larger than this characteristic length scale, it tells you that it's the interfilament frustration that's limiting the size. If it's smaller, it's the intrafilament frustration. Right? That's important if you want to understand what your predicted size would be in some experimental system. But for now, let me put it to this side. Okay. So I've introduced these two examples, and I won't go into any more detail here. There are more examples. There's probably about sort of 6 classes of, maybe now 7, of mechanisms that we sort of can classify as mechanisms of different types of order that can exhibit this geometrically frustrated assembly behavior. So on one hand, different types of order that is incompatible with Gaussian curvature. I told you about the competition or incompatibility between twist or chirality and some type of two-dimensional order and some fibrous material. There's a frustration between chirality and two-dimensionally layered materials, and also a kind of a mechanism that I'll call kind of an incompatibility between intrinsically curved shape and uniform spacing in kind of multi-layer stack assemblies. Okay? So all of these systems exhibit some sort of version of the phenomenon, or have been implicated to exhibit some version of the phenomenon that I showed you on the previous slides, although, of course, there are sort of subtle differences between them. So let me now change gears to sort of talk about, well, how kind of the physics finds a way, right? How do these systems try to avoid this kind of large energy costs of frustration? What are the mechanisms that allows these systems to escape frustration? So why is that important? Well, this is the story I started with, okay? I told you what's important here is that if you have a frustrated system, what that can lead to is an energy per unit area that grows with the domain size as some power law. And if we imagine some regime where frustration is sort of infinitely rigid, right? I can fix the frustration and there's no length scale or energy scale at which frustration can be avoided, this power law would keep going forever, okay? But in reality, in any physical system, there's going to be some upper limit, okay? So you can imagine now in this toy model I suggested, you know, there's going to be some finite elastic energy cost that I need to pay to take these warp puzzle pieces and just deform them back to some compatible shape, right? I'll just deform them back to rectangles. And now the energy density associated with that flattening, right? If this power law were to exceed that, it would tell you that there's a lower energy solution, okay? So what this means is that if you have such a shape flattening mechanism, right, to sort of expel frustration, that you should expect, in general, some sort of length scale and some crossover from a power law to some sort of saturated energy density, or a normalized energy density for assembly. Okay, and so this introduces a length scale that I call the escape length, because what happens when a system is able to assemble beyond this size, it starts to look just like an unfrustrated assembly again, okay, and it can grow to infinite size. So why is this important? Well, again, it tells us about really what's the upper limit, the sort of maximum self-limiting size we could expect an assembly to achieve. And it sort of defines, if you like, the width of this, this boundary between the self-limiting phase and the bulk phase. Okay. So let me give you an example, again, in the context of this initially very simple model of spherical caps, crystalline caps. So the first model I told you, I said, I'm forming a crystalline assembly on a sphere, but the sphere is not allowed to change shape. Okay? This, of course, is not very realistic for a number of applications. So for example, if you had a crystal forming on a liquid interface, there's some finite free energy cost to change the shape associated with surface tension and pressure. And of course, if you have an assembly of shell favoring proteins, there's some finite energy cost to just flatten them out to grow a planar crystal, right? If frustration is such a problem, why not just expel the Gaussian curvature? So in our model, we're going to introduce one new term. These first three terms are the same that I described previously, now looking at the free energy per unit area. But I'm going to introduce a simple elastic energy model that says there's some preferred frustrated shape, but the substrate, if you like, is allowed to flatten out if it wants. Okay? So if you study such a model, you find exactly the scenario that I described before, that the elastic energy as a function of area has this generic crossover where I go from some power law growth that I described previously to some renormalized elastic energy density where that sort of extra energy density is just the energy I needed to pay to set the Gaussian curvature to 0, just to flatten out my puzzle piece, if you like. Okay, and that crossover occurs at some, in this case, at some length scale that depends on the ratio of some moduli for shape flattening versus the frustration energy. Okay, but in this particular model, it gives you what controls this length scale. So if you put this back into the thermodynamic theory I described before, okay, you can compare the self-limiting size as a function of the drive to grow this crystalline cap. If frustration is unavoidable, these structures are predicted to be self-limiting at all sizes, whereas if they're soft, they're only self-limiting up to some critical amount of chemical potential drive, at which they undergo either a first or second order transition to a bulk phase. Okay? And so this is the origin of this kind of this type of phase diagram that I described to you previously on the first slide. It's the sort of interplay between these three mechanisms. Let me give you one more, maybe two more examples of these these frustration escape mechanisms. The second one is not associated with sort of flattening out or avoiding frustration, but instead it's associated with changing the topology of the assembly. okay? So one way that spherical crystals can avoid these kind of prohibitive costs of growing larger and larger is that they can change their internal order. Okay? So for example, instead of making a perfectly hexagonal crystal, what turns out to be favorable to do is to take my hexagonal crystal, cut out a 60-degree wedge, and glue it back together. And that leaves me with the following type of defects, shown here in red. This is a 5-fold disclination. Okay? So this one only has 5 nearest neighbors, everyone else has 6. And it turns out that this modifies this kind of this Fabel-von Karman or elasticity theory formulation in the following sort of nice way. So the equation that describes the generation of stress in this mechanical sheet, it has 2 sources of stress now. One of them is coming from this distributed Gaussian curvature. Okay, this is a homogeneous, uniformly distributed source of stress. So this is like a uniformly charged charge density in your E&M problem. Okay, and a monopole-like charge coming from these topological defects. The amount of charge is, the sign of the charge is dependent on whether it's a +5 or a +7 defect. Okay, but the essential heuristic idea here is that what topological defects are trying to do is kind of screen the far field elastic stresses that are generated by Gaussian curvature. And so what people have been thinking about is that what the number of defects you should expect to find is basically the number of defects that sort of neutralizes the effect of Gaussian curvature in this electrostatic analogy. And that's sort of true. And what I love to advertise here, actually, this is work that is yet unpublished by C.U. Lee in a little bit of a collaboration that we've actually just begun. So if you look at the elastic energy as a function of the width of the crystal, what you find is that this energy density branch for a defect-free crystal, again, indeed, it grows infinitely large. But at some point, this elastic ground state crosses over to one where you have a single 5-fold defect. You increase the curvature further. You have 2 disclinations, 4, 5. And eventually, you go far enough that you get exactly 12 5-fold disclinations. And what I have to advertise here, it was only until, I don't know, a few months ago that sort of a theory was sort of in place that was able to sort of cover the evolution of a sort of perfect, unfrustrated, defect-free crystal in its flat state to a crystal that can cover the entire solid angle of a sphere. Okay, but what you find at the end of the day is that this is a sort of a more rugged way of renormalizing the energy density of this crystal, but eventually you have some crossover at a length scale, in this case that's defined by the amount of curvature, from a power law growth to something that's kind of plateaued. Okay. So I won't say anything here in the interest of time, but just to say that these chiral filament bundles have versions of these mechanisms here. There's a version of shape flattening that you can think of as just untwisting the chiral interactions that expels frustration. Chiral filament bundles, it turns out their ground states also favor the similar distributions of topological defects that tend to try to screen these elastic stresses. So this phenomenon is at least somewhat generic. What I would like to do, but need to know how much more time. Oh, 10 minutes, great. Okay, perfect. Is describe one last mechanism of trying to escape frustration. That's not associated with shape flattening. It's not associated with reorganizing the interior of the assembly, but it's associated with reorganizing the boundary of the structure. Okay, and so to introduce this, I want to sort of motivate it by thinking of this kind of this problem. I think about this. I have young kids in the house. If you have an injury on your elbow or your knee and you need to put a Band-Aid on it, okay, you need to take something that is stress-free in its flat configuration and force it to conform to a surface with a non-zero Gaussian curvature. Okay, and I already told you that Gaussian curvature leads to stress in that sheet. So you can ask yourself, well, if I have a certain area that I need to cover, what's the shape that minimizes the amount of elastic stretching in the sheet to conform to your knee, right? Okay, so it turns out this is an ill-posed problem, but let's neglect that for the moment. So what you can imagine is comparing the elastic energy of this compact assembly, right, a circular disk. And I've showed you that the elastic stress is growing as the width of that crystal squared, the radius squared. That tells you that the elastic energy is growing as the third power of the area. So it's growing with the number of particles cubed, a huge energy. Okay? But if I take those same number of particles and I reorganize them, I'm going to have to lose some cohesive bonds in order to do that, but I can spread them out so that there's a thin direction, like in a strip, and a long direction. You can show that the solution of this von Karman equation has the following structure, that the stress drop takes place along the narrow direction of the crystal. Okay? So in fact, in this case, the stress is only growing with the smallest dimension of the structure. Okay? So the stress is only growing with the width, so that tells you that you can go to a situation where the elastic energy is only now growing as the area. You're going to have to pay some cohesive energy associated with breaking of bonds at the periphery, but you should expect some sort of transition between them. And in fact, this was predicted by Gomper and Schneider well over 10 years ago, and they were interested in initially thinking of a model of these crystalline domains of lipids in fluid-solid composite vesicles. They argued that this transition can be controlled by the ratio of the sort of line tension at the edge of this crystal that can reorganize its two-dimensional area versus the elastic modulus. So when you get to very high line tension, you should expect compact circular caps. But at low line tension, the elastic energy causes these caps to spread out into belts. Okay. And what I can show you now is, in fact, that this is exactly what was been observed, and this is an experiment by Vinny Manoharan's group at Harvard. What I'm showing you is a crystallite that's on the surface of a very large, at least large compared to the diameter of these micron-sized particles, very large droplet. You see hexagonal crystallites that if you look at enough of them in enough movies, you say that they're growing kind of quasi-isotropically or at least hexagonally. Okay? Whereas if you get to some small enough crystalline size, these crystals branch and become anisotropic. Okay? So the measurement confirms that this size here, this narrow size, is in fact decreasing as predicted with curvature. Okay. So this is yet another mechanism of escaping frustration. We were interested in sort of how this might play out in the context of the second kind of prototype model in these filamentous bundle systems. And so now let me just kind of quickly introduce the simulation model that Doug Hall used to explore this question. Essentially, he considered twisted filament bundles with some bending energy costs for deforming the filaments away from a straight shape, and some pairwise interaction between all the filaments in the bundle, where we consider both some potential energy with some controllable depth, but what's more important is controlling the range of that interaction. So if I have very short-range cohesive interactions, I can make the model more brittle. If I have effectively longer-range interactions, I get a ductile potential. So what's essential in this particular parameter is it allows us to tune the ratio between the line energy and the elastic modulus in this model. Okay, and so what Doug does is he considers bundles that have different hexagonal cross-sections. They can be wide, fat, thin, and so forth, and calculates the energy density. Okay, so this is an example of a fairly ductile simulation condition where you're looking at here a map of the energy density of this structure as a function of its dimensions x1 and x2. It may be hard to see in this picture, but there's a single energy minimum sitting in the middle here, which tells you that this filament bundle wants to be about 36 filaments wide in both of its transverse dimensions. Okay, again, many, many times the diameter of individual filaments, but quasi-isotropic. However, as we sort of tune the range of that potential down so that the interactions become fairly brittle, if you like, this elastic modulus goes way up, what you see is that this energy landscape sort of splits into two nearly degenerate minima, where the large dimension of the structure becomes much, much larger than the smaller dimension of the structure. Okay? So the filament, the bundle becomes a ribbon that's sort of still about 36 filaments wide, but it becomes narrow, only 10 filaments across. Okay? So what appears to be happening here is sort of an analog of the mechanism I described before. So the system is trying to avoid the cost of this interfilament frustration. And so what it's doing is it's reshaping the boundary, introducing lots of excess boundary that relaxes the constraints of geometric frustration, lowering this interfilament metric cost, but it doesn't quite get away from frustration, right? It doesn't grow infinitely large in this direction. It still stops. And so what's going on? Well, if you look now at the bending energy, this is the cost of deforming the shape of the filaments away from straight configuration, this is still growing with the largest dimension of the structure. So what you find is a situation where somehow, there's two mechanisms of frustration. The assembly sort of finds a way to escape one of them, but in some way, if you like, it's reinforced by some secondary mechanism that holds it back. Okay? And this is actually a kind of a very nice situation where in this limit, the sort of kind of different dimensions of mesoscopic dimensions of this material sort of decouple and depend on two different material parameters. One, the thickness dimension depending on the interfilament elastic modulus, the width dimension depending on the bending modulus. Okay? So if you have ways of measuring these structures mesoscopically, it gives you a way of kind of working backwards to understand what are these kind of molecular scale parameters. And so in the interest of time, let me stop here and acknowledge, summarize for a second. Okay, so what have I told you today? I've told you, and hope I've convinced you, that geometric frustration gives rise to some what I'll call anomalous assembly properties, assembly that you can't get in canonical unfrustrated systems. In particular, perhaps maybe most attractive, sort of self-limitation at a length scale that can be, in principle, arbitrarily larger than individual building blocks. However, the extent to which the system can actually realize geometrically frustrated self-limitation is limited by a number of kind of competing morphological mechanisms that try to avoid or escape frustration. Okay, so why does this matter? Why might this be useful? So I didn't tell you about this, but this is kind of a little bit where we're thinking. Why should we try to understand this? Well, if we had a way, for example, to sort of program building blocks with a controllable amount of frustration, such that simply by self-assembly, we can get them to assemble into finite structures as opposed to infinite structures like crystals, this would be useful. Okay, how do we know this will be useful? Well, we know it would be useful because biology has somehow invented ways of taking proteins, building blocks, and disassembling them and reassembling them into different superstructures of different size controlled distributions in different materials. So for example, if I take collagen that forms in my cornea versus collagen that forms in my tendon, it's all made out of fibers and bundles, but the size distribution of that same material has been regulated to a different size range. Okay? So we take the same building blocks and we adjust the material properties purely through control of the multi-scale dimensions of that material. And there are a range of kind of functional properties for which it would be attractive to have materials that you could build in a laboratory that could kind of realize some of this sort of material property control purely through the kind of programming of the structure through its frustration at the building block scale. So with that, let me stop here and acknowledge a range of collaborators and funders who've been generous enough to fund a lot of this work. Most notably, Doug Hall, whose simulations I showed you previously, Isaac Bruss, a former student, and again, CU and Roya, whose work I showed you somewhere in the middle. And with that, let me thank you for your attention and take any questions you might have. Yeah. Yeah.
So how different is this and what's the big difference?
Yeah, so I think the difference, so I don't know, I mean, part of the answer is I don't entirely know sort of the difference in terms of I think the mathematical models are going to be very similar, right? So what's different in the context of assembly and a lot of soft matter systems is that these order parameters sort of emerges collectively from the building blocks themselves. So for example, for this kind of epitaxial frustration, you need a substrate, right? So frustration, if you like, is imposed as an external field or some surrounding medium, okay? These materials are somehow frustrated by themselves, right? That's to say they don't need, if you like, a boundary or a boundary condition to frustrating them.
But there are also bulk phases which have built-in incommensurability. This could be large period. I mean, there are no crystals, and there are also magnetic orders with spiral.
Yes. So I mean, again, I guess the sort of concept. So I would say, what's the real? I think there are a lot of mathematical descriptions. So for example, I may be even going further back. So this whole story about these topological defect configurations on curved crystals. I mean, this is some version of what. This is like an Abrikosov phase of, and so the mathematics of these systems shares many features. Okay, what is maybe particularly surprising and useful is that, again, you don't need an external field. You don't need boundary conditions. I don't need to apply a field. It's somehow intrinsic to the structure and interactions of the bricks themselves in ways that we don't understand, but I think that's the concept. Yeah.
I have a question. So this sphere that you showed that there are, like Vinny's experiment, that there are holes on the sphere. So there are like flow discriminations on his experiments, or why there are holes? Is there any measurement of these holes? Or?
There are measurements of the structure of those. So what? So they've measured, for example, the fractal dimension of the structure. It's not clear, and I think probably very unlikely, that what you're looking at in those experiments are equilibrated states, right? And so what happens is these particular patterns form that the crystal's kind of nucleated, and it's growing and growing and growing, and then it reaches some critical size at which it starts sort of jetting out branches, okay? It's not they basically never observe that these branches kind of break off and reorganize and anneal over long times. And there's some, again, I think we've talked a little bit about that. There's some question about whether or not that experiment sort of is telling you that there's a regime where the system is always going to try to avoid defects, for example, or somehow it's been been selected out by the kinetics. So this will maybe just another way to sort of just answer this question. So what I told you about today, at least in terms of what we understand from the kind of physics of these systems, is really based on the equilibrium ground states of the system. So we have some understanding about like what those equilibrium ground states are. We have a little bit of understanding how one equilibrium ground state is like maybe kinetically or kinematically connected to another one. We know very little about the non-equilibrium physics of these systems. So for example, what you expect is that you're going to have a very complex energy landscape with different, if you like, basins that are associated with these different morphologies. And it's very likely, and in fact, every experiment that's conducted is pretty far out of equilibrium. And the question is, what is it about the sort of nature of those landscapes that's likely to funnel you towards or away from one self-limiting morphology or another? That it's not been studied. There are a lot of questions.